So this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on matrix inverses. We're really talking about the multiplicative inverse of a matrix. So what is that? If I have a square matrix A, its inverse is denoted A to the power of -1. It's another square matrix such that when you multiply them together, you get I, the identity matrix. And when you multiply together a matrix and its inverse, it doesn't matter the order in which you do it, you always get the identity matrix. So remember, the identity matrix is a square matrix that has 1 along the leading diagonal. Each diagonal entry is 1, and all other entries are 0. The identity matrix is important because it is the matrix, when you multiply by it, you don't change the original matrix. It preserves the identity of a matrix under multiplication. So why is this important? Let's say I have the equation A times B equals C, and I want to find what B is. So if I want to find what B is, and A and C were just numbers, this would be easy as I would just divide each side of the equation by A. But division is not defined for matrices. So if A, B, and C were matrices, I can't divide each side of the equation by A. I can get around that, however, if I multiply each side of the equation by A inverse. So it's important that you know whether you're pre or post multiplying. Here I'm pre-multiplying, I'm multiplying at the start. So if A inverse goes at the start on the left-hand side, it has to go at the start on the right-hand side because matrix multiplication is not commutative. So A times its inverse, or A inverse times A, just gives me I. So the left-hand side just becomes B, and I have solved the equation. So that's why inverses are important. So I said before that A needs to be a square matrix. Only a square matrix has an inverse, but not all square matrices do have an inverse. Okay, so if it has an inverse, it must be a square matrix, but if it's a square matrix, it may not have an inverse. So just for interest, if a matrix is not a square matrix, it may have a left inverse or a right inverse, but not a two-sided inverse. So let's say X, for example, was a 3 by 2 matrix. There may be a matrix Y, which would have to be 2 by 3, that gives you the identity, but Y times X, the other way around, would not give you the identity. So that's why we're looking at square matrices. So rectangular matrices that are not square, they may have a left inverse or a right inverse, but they won't have a two-sided inverse like this. All right, let's go through how to actually calculate the inverse of a matrix. So I said before that not all square matrices have inverses. So how do I know if a given square matrix will have an inverse? Well, I need only look at its determinant. If the determinant of a matrix is anything other than 0, it will have an inverse. And if the determinant is 0, there is no inverse. So our first step when calculating an inverse by hand should be to calculate the determinant to tell us whether or not there actually is an inverse. So it turns out calculating the inverse of a 2 by 2 matrix is actually very simple. So if I have a 2 by 2 matrix A, and I'm going to call its entries A, B, C, and D, it turns out its inverse is 1 over AD minus BC, so that's just a scalar, and then what you do is you switch the two elements on the leading diagonal and change the sign of the off diagonal elements. So hopefully you note that this here is the determinant of a 2 by 2 matrix. Now this makes sense. If the determinant was 0, this number out the front of the matrix would be 1 over 0, which can't happen. So this is a formula, a really easy formula to find the inverse of a 2 by 2 matrix. Let's look at a quick example. So let's say I have this matrix here, A equals 1, 2, 3, 4. So little a is 1, B is 2, C is 3, D is 4. So A inverse will be 1 over the determinant, which is 1 times 4 minus 2 times 3. So that's minus 2, so it's clearly not 0. It will have an inverse. And then you swap the two elements on the leading diagonal and change the sign of the off diagonal elements. How easy is that? So it doesn't really matter whether you go and multiply each element in a inverse by this scalar. I'm just going to do it to show you. And that will be the inverse. So if I multiply this matrix here by this matrix here in any order, I will get the 2 by 2 identity matrix, which is this one here. Okay, so you can multiply them together if you want to check. So unfortunately, it isn't that simple when we're dealing with matrices of a higher dimension. 2 by 2 matrices are easy. Even 3 by 3 can be quite complicated. So I'm going to show you two methods you can use on higher dimension matrices. The first method that I will show you as to how to calculate the inverse of a matrix that's larger than 2 by 2 is by calculating its adjugate matrix, and we use this formula here. So let's look at this matrix here, A, and we'll show you how to use this method. So the smart thing to do is first calculate the determinant of A. Not only is that part of the formula, but it will tell us whether or not the matrix A can actually be inverted. So we'll calculate the determinant of A using cofactor expansion, and once again I will expand along the first row. So we take the first element of this first row, cross out all the elements in the same row and column as it, and we multiply that element by the determinant of the matrix that's left over. So the determinant of that 2 by 2 matrix is 1 times 0 minus 6 times 4. Okay, then we move on to the next element in the first row of A. So we go along to this element here, cross out everything in the same row and column as it, and we multiply it by the determinant of the resulting matrix, which is 0 times 0 minus 5 times 4. But remember, every second one in this calculation, in cofactor expansion, it needs a negative in front of it. So it would be minus 2 times minus 20. Go along to the next element, cross out everything in the same row and column as it. This one will be positive. And we find the determinant of the resulting matrix here. So it'll be 0 times 6, which is 0, minus 1 times 5. So if you put that all together, you get 1. So the determinant of matrix A is 1. That means it can be inverted. So our next step is to calculate the adjugate of matrix A, which is actually quite complicated. In fact, what we're going to do is calculate its transpose first. So I'm going to call the transpose of the adjugate matrix A B. So B will be the same size as A. It will be a 3 by 3 matrix, and we need to go and calculate its elements one at a time. So how we calculate each element is similar to what we were just doing in the determinant calculation. So for element B11, the element that will go in row 1, column 1, you find the element in A, A11, cross out all of the elements in the same row and column as it, and the entry in the matrix is just the determinant of the matrix that's left over. So 1 times 0 minus 6 times 4, which is negative 24. Here we don't times it by the original element. So we now go and do the same for the other elements in B. So the element in B21, so what we do, go to element A21, cross out everything in the same row and column as it, and we find just the determinant of the resulting matrix. So that would be 2 times 0, which is 0, minus 3 times 6, negative 18. I don't times that by 0, the original element that I started with, which is kind of what I was doing when I was finding the determinant. So if I now wanted to find element B31, I go to the entry in A in row 3, column 1, cross out all of the entries in the same row and column, find the determinant of the resulting matrix. That'll be 2 times 4 minus 3 times 1, which is positive 5. And I keep following this process until I have all 9 elements of matrix B. We simply put all of these entries into a matrix. So this would be matrix B, but just like when we were calculating the determinant, we have to go and change the sign of every second element. So this one here would become a plus. So we skip this one here we change its sign, skip the next one, this one here we change its sign, skip the next one, this one here, change its sign, skip the 5, and change the sign of the 4. So this is what B would look like. And the adjugate of A, remember this was the transpose of the adjugate of A, the adjugate of A will just be the transpose of this. So this matrix here in black is the adjugate of A. Now normally we need to times by 1 over the determinant. We need to times each element of the matrix by that. But here the determinant was just 1. So this is just 1 times the adjugate of matrix A. Therefore this here is the inverse of A. And if you times that by A, you will get the 3 by 3 identity matrix. So you might like to go and multiply them just to check. Now I'll show you the last method for finding inverses. So the last method we're going to look at is also useful for matrices larger than 2 by 2. So it turns out if we augment a matrix A and the identity matrix, that's row equivalent to the matrix that has I augmented with A inverse. So let's show you what I mean by that. So let's say I have the following matrix. So I have this matrix here, A, I want to find its inverse. So what I can do is I can augment this matrix A with the identity matrix. So it will look like this. So you can see that the left-hand side is A and the right-hand side is the identity. So what I do is I row reduce it. So this side becomes the identity and then this side here will become A inverse. So I'm just going to perform the same row operations that we've been performing all throughout this course. So my goal here is I want to make this side, I want to perform row operations, so this side becomes the identity. So I start by making this entry 1, so I did that by subtracting row 2 from row 1, and this is my new matrix, and I keep performing those row operations over and over. So my next step is to make this element here a 0, and I subtract 2 lots of row 1 from row 2 in order to achieve that. So I keep going and eventually I end up with this. So when we end up with this, of course left hand side is the identity and this is our inverse. So A inverse is the 3 by 3 matrix on the right hand side here. So that is A inverse. So note that this side of the matrix, if it's invertible, will always be able to be reduced to the identity matrix, because it turns out that any invertible matrix is row equivalent to the identity matrix. In other words, a matrix is invertible if and only if you can perform row operations to reduce it to the identity matrix. Reduced row echelon form of any invertible matrix is the identity matrix. So that's why this process here works. So again, if you multiply A and A inverse together, you will get the identity matrix. So that's why the matrix in red is the inverse of A. Right, there's just one more thing I want to quickly go through, and that is to do with the uniqueness of the inverse of a matrix. So it turns out that if a square matrix has an inverse, that inverse is unique. So that means if you have an invertible matrix, say A, there is only one matrix you can multiply by A to get the identity matrix. So if I have a situation where AB is equal to AC, let's say they both equal I. So that would mean B and C are both inverses of A. If that's the case, then B and C must be equal. That's very easy to prove. I can just pre-multiply each side by A inverse. It turns out the cancellation law for matrices holds when we're talking about invertible matrices. If A is invertible, you can cancel it out of an equation like this. So that's why studying whether matrices are invertible or not is so important. So if AB equals AC, then B equals C. So that means that if B and C are both inverses of A, they must be the same. Or in other words, the inverse of a matrix is unique. So what is not as obvious is, let's say I have CA is equal to AB is equal to I. That if a square matrix is invertible, that its left and right inverses must be equal. So this can actually be proved quite easily as well. So let's let B equal IB. The identity times B gives B by the definition of the identity, but CA is equal to I. So I can replace that with CA, and remember I can put the brackets wherever I like because matrix multiplication is associative, so I can change that to C times AB, but AB is equal to I. So B must be equal to CI, which is just equal to C. Okay, so that shows that if a square matrix has a left inverse and a right inverse, those inverses must be equal, further showing that the inverse of a matrix is unique. All right, this has been the luckiest maths teacher in the world. Have a great day.